Hey everyone, my name is Karpur Shukla. I'm currently a first-year PhD student at the Laboratory for Emerging Technologies at Brown University, and I'm recording this talk for the CCC workshop on physics and engineering issues in adiabatic and reversible computing. Before I begin, I want to thank the other organizers and CCC for inviting me to be a part of this, and I really want to thank many of the people I've reached out to, whose work is very much the foundation for what this is trying to achieve. I'll mention them explicitly later on in this talk. I'd like to spend a little bit of time talking about one of the tools that we can use to examine the properties of classical reversible computing using non-equilibrium quantum thermodynamics. So some of this might be a little bit elementary for some of the attendees, but I'm hoping this can give people in the physics session a sense of one of the approaches we're trying to take and how it fits into the broader picture. I'm also hoping this can give people outside of the physics session a glimpse as to the current questions we're looking at. I'll be focusing specifically on the GKSL or Lindbladian approach with multiple asymptotic states. I don't mean to give resource theories, shortcuts to adiabaticity, or quantum speed limits short shrift, because those are also hugely important. Luckily, others will be discussing those subjects in the physics breakout session, so I can focus this talk specifically on some of the finer points of this approach and its relevance to the theory of classical reversible computing. We'd really like to examine fundamental thermodynamic bounds on classical reversible computational processes, which means that we need to employ the techniques of quantum thermodynamics. We'll start by representing computations as operations on quantum states. Traditionally, examinations of the Landauer limit have started with looking at thermal operations on quantum states specifically, so I'll start with discussing those. These are defined as operations on density matrices of a system which are evolved in this specific way, where the system is coupled to a bath at a thermal state, the overall system is evolved over time, and then we trace out the bath. In particular, we require the evolution to always commute with the Hamiltonian. I'm not going to get into it now, but there's a proof that otherwise the time evolution costs energy to perform. So thermal operations are really defined from the outset as those that don't require external work or coherence sources to run. Alongside this notion of thermal operations, to represent classical information processing specifically, we can use a setup of n distinguishable density matrices, encoding a classical alphabet of size n. I'm lifting this encoding directly from some of Neil Anderson's previous work, so thanks to Neil for explaining this approach in his previous work. If we can exploit the property that density matrices form a convex space, we can decompose these into linear combinations of other density matrices, and thus an equivalent representation is of computational states represented as a decoherence-free subspace or decoherence-free subspaces in a larger system. The advantage of doing this is that you can then use individual density matrices in these subspaces to describe the microstate of the system, and the subspaces as a whole can describe the computational state. That way, we can separate evolutions that change the computational state from those that don't, and describe evolutions that do both. Special thanks also to Victor Albert for pointing out the equivalence of these approaches via the convex linear combination property to me. Sorry. All right. Using thermal operations, we can get an explicit non-equilibrium bound, which is this expression here. It's a little bit difficult to see in this form, but this just says exactly what we expect, that it's the ejection of information in correlated bits specifically that gives us the lower bound on Q. This is from a paper by John Gould, Mauro Paternostro, and Kavan Modi in 2015, and it's been improved on by several works, both by Gould Group and others, including Philippe Feist. I'm sorry for mispronouncing these names. Anyway, so this bound, this is the last equality in this expression, says that this bound depends entirely on the degree of non-unitality of the evolution. This is also this script n sub b down here, which looks at this sum of Kraus operators times their conjugates minus the identity over the environment. Just as a reminder, quantum channels are unital if they map the identity to itself, and we can check whether it is unital if the Kraus operators satisfy this specific relation here. I'll get to Kraus operators in the next slide for people who are slightly less familiar with it. Unital channels are not to be confused with unitary channels, which is when we sandwich rho on both sides with a given unitary. Unitary channels are a subset proper of unital channels generally. And before I move on, I just want to point out that this expression satisfies this idea that if it's unital, there is no lower bound on dissipation. So the dissipation, the lower bound on the dissipation is 0 if we have a unital quantum channel taking the initial state to the final state. Since Kraus operators might not be totally familiar to everyone, basically these are operators which capture in some sense the effect of the overall SP evolution on one of the subsystems specifically, if we just narrowed our focus on that subsystem. The overall SP evolution looks similar to what we said for thermal operations, but it's more general. We don't need B to start in a thermal state, and we don't need any restrictions on the commutator of U and H. We can define the Kraus operators via the partial trace over the bath, and then just doing the spectral decomposition of U in the bath eigenstates each time U pops up. This is an incredibly useful expression, since it gives us a way to characterize what it would look like if we looked only at either the S part or the B part of this overall evolution. On this slide, I'm looking at how the system state evolves in time, so the relevant Kraus operators are acting on the system. I'm referring to these E sub jk's as the system Kraus operators just for specificity. Normally, these are just called the Kraus operators. And the reason these are normally called the Kraus operators is because ordinarily they're just, people only look at the system evolution. But the non-equilibrium Landauer limit on the previous the previous slide is actually expressed in terms of the bath evolution and the bath. This traces over both the system and the bath, but the bath evolution it's described in terms of the bath Kraus operators, which is why I specified. Occasionally, you will see people using bath Kraus operators. The maps on density matrices that result from the Kraus operators are what are called completely positive trace-preserving maps. And this is the most general category of map that still satisfies quantum mechanics. Here, complete positivity means it's positive. It's positive if you embed it in a larger system. And trace-preserving is trace-preserving. So the trace of the density matrix stays constant over time, which is what we want in quantum mechanics. It's worth noting that the Kraus operators map here system density matrices to themselves via the operator algebra operation, but they depend entirely on the bath eigenstates. Since they depend on the bath eigenstates, they're not unique. You can do any unitary transform of the bath eigenstates and get the same result. This brings us immediately to the first tool we'll be using to examine the time evolution of reversible computation operations, which is the Lindbladian or GKSL evolution. If we take the Markov approximation to time evolution, so if we take the Markov approximation to time evolution of the density matrix, we have the density matrix at time t plus dt depends only on the evolution, only on the density matrix at time t plus the Kraus operators at time d over the interval dt. From this, we can expand the channel, the quantum channel that maps rho at t to rho at dt in powers of dt, and we can define the Lindbladian or GKSL evolution as the evolution that comes at lowest order in dt. The evolution of the expansion, the expansion of the evolution in dt naturally corresponds to the expansion of the Kraus operators in dt, which defines what are called the jump operators f, here f sub L. These let us recast the Kraus operators in terms of a differential equation for the time evolution of rho, which is the Lindbladian or GKSL equation. This is the quantum master equation or the quantum Markov equation, and it serves as a starting point for a lot of stuff in quantum optics and open quantum systems. Just a couple of brief points to note. The first term in the sum has jump operators acting on both sides of the density matrix, here, this term here. So it's often called the sandwich term. The sandwich term induces one of the jumps outside of the system Hamiltonian, whereas the other terms in the sum normalize the process in the case of no jumps, normalize the process in the case of no jumps happening. Without the sandwich term, the rest of it has operators acting either to the left or to the right of the density matrix. So another standard way of thinking about this equation overall is to collect everything except the sandwich term into a non-Hermitian Hamiltonian, and treating the sandwich term as restoring the CPTB properties we want in quantum channels. Unsurprisingly, the formal solution to this expression here, d rho ds equals L upon S, is just e to the TL upon the initial rho at the initial time. So we have the formal expression for rho at time t as just e to the TL upon the initial rho. We can then define the asymptotic or the steady states of the rho as the states that the asymptotic or steady states of L as the states that survive in the infinite time limit. Since the Hilbert-Schmidt norm lets us impose a vector space structure on density operators, we can recognize L as just an operator on Hilbert space operators, which is normally called a superoperator. Then we can look at the Jordan-Chevalier decomposition of L. Ordinarily, people assume that they're working in a system with just one steady state, which is the right eigenvector of L, whose eigenvalue is 0. But there's nothing really stopping the spectrum from having several imaginary eigenvalues. And in the infinite time limit, these obviously wouldn't decay like the ones with real part less than 0. So there's nothing stopping L from realizing an entire subspace of asymptotic states, which can support its own non-trivial dynamics internally. This is the framework of multiple asymptotic states developed by Victor V. Albert alongside Liang Jiang, Martin Frost, and Barry Bradley. I'm really, really sorry for mispronouncing names. I'm going to talk about it. I'm going to talk a lot more about this framework in the plenary talk, since I think this will be a really vital framework for examining some important dissipation bounds on reversible operations, both classical and quantum. For now, I'll leave the discussion of the asymptotic decomposition here, the actual asymptotic decomposition here. I'll discuss a little bit more about this in the plenary talk, and move on to the Berry phase, which will lead us to the quantum geometric tensor. The quantum geometric tensor is also a crucial component of the dynamics of multiple asymptotic states, so I want to give it a proper exposure. I'll do the Berry phase and curvature the standard way. There's an equivalent formulation in terms of something called the Kato Hamiltonian that's more natural for operators, but I think it's also less familiar. We'll start with the normal expression for time evolution of a state, in the non-degenerate adiabatic approximation given here, and say that the parameters that the Hamiltonian depend on live in a parameter space. Then, if the Hamiltonian ever returns to its starting conditions, it's pretty straightforward to derive that you can get a phase factor which can't simply be scaled away, which is our familiar Berry phase. If we then have degenerate eigenspaces, the phase is no longer a single number, but now a UN matrix, and the quantity that we're interested in is the trace of the path-ordered exponential, sometimes referred to as a Wilson, or I guess the trace of Wilson. The derivation of the non-zero Berry phase expresses it in terms of a gauge-dependent one form analogous to the magnetic vector potential. This is often called the Berry vector potential, or the Berry one form, or the Berry connection. This is this A mu here. And it's given by the expectation value of d mu with a specific n eigenstate. The name connection just comes from the fact that this is an actual connection on the manifold of states, where we can think of this process of starting of adiabatically evolving the Hamiltonian, starting in a state, adiabatically evolving the Hamiltonian, and returning to the starting conditions. In parameter space, we can think of this as taking a state vector, evolving it around a closed loop, and returning it to the start. If the manifold has some underlying non-trivial geometric properties, we won't get back to the same state, since now we have a non-trivial Berry phase, and the Berry vector potential gives us the parallel transport information. Essentially, the Berry phase corresponds to the failure of the failure of the state to return to exactly the same state as it was before. So there's some non-trivial information in the parallel transport, and this information is given by the Berry connection, which is why it's called a connection. The manifold that's sketched out by the adiabatic approximation, in fact, gives us two important geometric quantities, the Berry curvature and the quantum geometric tensor. These both come from examining the distance between two states and decomposing this into a symmetric and an antisymmetric term. The antisymmetric term is the Berry curvature, which gives us the curvature of the manifold, and it is analogous to the electromagnetic tensor, this sigma mu nu here. Whereas the symmetric piece will end up giving us the quantum geometric tensor. We can notice that the quantum geometric tensor is formally defined as this symmetric piece minus a mu wedge a nu, and the reason is the reason is that the symmetric piece, this gamma mu nu, directly measures the distance between states. But in actual quantum mechanics, we're not interested in we're not interested in the vectors. We're interested in the rays, because we can arbitrarily scale it by the overall U1 global phase symmetry. So G mu nu, gamma mu nu is not gauge invariant. It has this gauge dependence on a mu and a nu, or a mu, and so G mu nu is defined to take care of this gauge dependence that arises from the fact that gamma mu nu really is looking at the states, whereas G mu nu is looking at the states modded with U1 modded out. Intuitively, if we an intuitive picture for ds squared is that when we're examining the difference between two states, we want to know their overlap, which is given by the quantum geometric tensor, and their relative phase, which is given by the Berry curvature. These quantities all have direct analogies on the manifold sketched out by systems with multiple asymptotic states, which I'll have time to get into a bit more during the plenary. Okay, so what was the point of all of this? Let's bring this back to classical reversible computing. The point was that we had a description of classical reversible computing in terms of a set of density matrices, which we recast as a set of decoherence-free subspaces. And we want to understand some of the basic properties of this, including things like dissipation bounds and entropy production rates. If we consider GKSL dynamics with multiple asymptotic states, the asymptotic subspace can realize non-trivial dynamics, And this can let us examine classical reversible operations the way we set up in the beginning. Attendant with the non-trivial asymptotic subspace comes the quantum geometric tensor on the operator space. And this is going to show up in some of the dissipation bounds we're interested in examining for classical reversible computing. A couple of notable ones, which I plan on discussing in the plenary, are the thermodynamic uncertainty relations, which talk about the relationship between entropy production rates and conserved currents in terms of the information properties of the conserved currents, and what's something called the thermodynamic length, which talks about the minimal dissipation for quasi-static processes. So that brings us to the end of what I wanted to, the main thing what I wanted to talk about for the plenary as a whole. The rest of it I'm planning on discussing a bit more in the breakout session. Before I go, I would very, very much like to thank and acknowledge the Computing Research Association and CCC for inviting me to help organize this and be a part of this and to talk here. I'd like to thank Hannah Watson, my fiance, for supporting me through all of this. I'd very, very much like to thank Michael P. Frank, who's been helping me out immensely in helping me develop this system, my advisor, Jimmy Shu, Victor B. Albert, who's also been helping me develop this framework and who developed the initial framework of multiple asymptotic states, and several other people that are listed here who I've been in contact with, who have been helping me with some of the, who've been either helping me or have had initial conversations with them on attacking this problem of the theory of reversible computing in using different quantum thermodynamic approaches. Again, many of these people, or some of these people, will be speaking at the breakout session, and I look forward to further discussion. Also, finally, I'd very much like to thank you for your attention.